And when people die, it's kind of like whatever. What was that girl's name?
People die, it's like whatever.
She died, I was like, oh, whatever.
I don't like her anyway, so it's just like, you know, she died, I don't care, whatever.
The wife died, whatever.
Okay, so
Yeah, we had so much fun.
I might throw some more in this, but so far what we know is on test 3 is given a matrix, find its eigenvalues, eigenvectors, you should be able to diagonalize it. Find powers of the matrix. And solve a system of first order ODEs using eigenvalues, eigenvectors. Did we actually do this?
Yes.
Yeah.
Good stuff? I don't know.
Maybe it should be on the test.
It's all a blur. Because I covered a lot of the same ground in Math 392, so sometimes like, did I tell these guys or did I tell those guys? That happens sometimes. Yeah, and this would pretty much be one problem. So it's like a part A, a part B, a part C, and part D. For test 3, I'm gonna do it with a 2x2 just to make sure you know how to do it. On the final, I'll probably do a 3x3 for this question. But I won't go higher than a 3x3. The other thing we need to know is
I like these standards.
what else is there? There's going to be, I don't know what we want to call these. Change of bases of linear transformations. Basically, if you've given the outputs for certain vectors, find the linear transformation. And compute the output of some other vector. I think it was Spring 07, problem 8 was that one, where they told you that L of blah is blah, and they told you a bunch of those, and they say find L of this, and then find L of this.
The example that we did in class.
Right, so similar to the example that we did in class. I don't know exactly what to call that kind of problem, but that's the one. So done in class. Be able to work in any given basis. The third thing is So I'll give you one of those problems again that was on test 2 to see if you guys can redeem yourselves if you didn't do well. So yeah, that's pretty much all I plan on doing. I could throw in, if you guys want, some easier stuff, some short answers, maybe true or false, but I haven't decided if I'm doing that. I know I'm putting these 3 on it. Just to fill up the time. May or may not, be prepared for them if they come. For the final, it'll look like one of the old ones. I'm not going to deviate from the format too much. There are some of the old finals that they don't really focus on proofs a lot. I'm going to give you proofs, so make sure you actually know how to do one of the ones that asks you to prove certain things. Proofs are there. I'll probably also make it 2 parts. We have a compulsory and then you have some choices. So definitely in the compulsory section, there are going to be all the computational things, you know, be able to find a determinant, find an inverse, solve a system, things like that. Choices, for choices, I'll put maybe a lot of proofs here, and you have to choose some of them. Like in the choices section, it'll be all proofs. And you just choose what proofs you think you can do. But everything computational is going to be here. Maybe a short proof might be here, or maybe no proofs at all. All the computational stuff, you know, inverses, determinants, solving systems, finding eigenvalues, eigenvectors, diagonalizing, forming a change of basis. Yeah, that's sort of it. I actually sent you some solutions this morning, email, some solutions of problems of this type. Like I went through the finals and I did all the ones that are of this type that we didn't do in class. So you can see the solutions there and you can ask me questions if you want. Or any other general questions.
That's your cue. Part of the homework, 5.1, 5C. So that I was finding the eigen
5.1, yeah?
Yeah.
What size is the matrix?
It's a 2x2, but like I ended up getting like zeros on the matrix. And it was just like
So
how
wait, before we go into the homework, the
Yeah.
percentage distribution of the second exam, which is going to is 15% of our grade. How much is each exam again?
I don't remember what the syllabus said.
Okay.
But this will count for 2.
And
Okay.
How many problems you got on the 2 tests?
3 or 4. Yeah. These 3 definitely, right? I'm definitely going to ask you about eigenvalues, eigenvectors, all that. I'm definitely going to ask you a question like this. I'm definitely going to put a proof problem about linear transformations. But I might throw in some short answers.
Yeah, but the question, they'll all be like interdependent, like you have to answer question, let's say 1 from here will answer question 2.
No, well, these will all be interdependent. So once I ask you for eigenvalues somewhere, I'm going to ask you for that same matrix to diagonalize it, for that same one to find the powers, for that same one to solve a system where that's the coefficient matrix. So everything with eigenvalues and eigenvectors, that's going to be interdependent. right? Because otherwise you'd have to recompute everything to do each problem. This one here, yeah, this will all be on its own. So it'll be a problem similar to this. So it has parts in it, but it'll all come from the same set of things. And this will be separate here. Yeah. The finals would look like one of the old finals, one of the ones that has proofs on it. Yeah. So the first part, I'm going to ask you to do all the computational stuff. The second part is the proof section, where I'm going to give you a bunch and you choose, I don't know, maybe 3.
So it's like 7 and then 3.
So it'll probably like, I'll give you 5 proofs, choose 3. Something like that.
Maybe we can do some exercises now with the proofs.
So I haven't actually written it yet, but I think maybe I put 70 points up here, 30 points here, 10 points per proof.
Can we do some exercises with proof now?
Will there be, will there be bonuses on the final?
No.
I think that's it.
But a bonus is on third.
Sure.
Will there be any proofs on the third exam?
Yes.
Proofs are life.
So what were you saying about 5.1?
The homework is it's a 2x2 matrix. It's an identity 2x2 matrix. So it's 1, 0, 0, 1.
Okay.
And it asks us to find the eigenvalues of the eigenvectors. But I ended up getting, after like I found the eigenvalues, I got 1 and 1 for both eigenvalues.
Wait, this was 5.1, and it was what problem?
5C.
5.
C.
Okay, but your A was the identity,
Yeah.
and it asked you to find the eigenvalues and eigenvectors. So basically, you look for the determinant of lambda I minus A. Set that equal to 0.
So it's a diagonal, so it should be empty.
Yeah. So it's going to be what? Lambda minus 1, lambda minus 1, 0, 0. And so you get lambda minus 1 squared equals 0, so you get both lambdas are equal to 1. Okay.
And then when you plug each one in respectively, you're going to get 0 by 0 matrix, 0 in the matrix, and then
Okay.
how do you find it?
Well, that means every vector would be an eigenvector. Right? So if lambda equals 1, then if you want to solve lambda I minus A times x equals the 0 vector, then you'd end up solving 0, 0, 0, 0, x1, x2 equals 0, 0. And this means every x1, x2 is a solution. Does that make sense?
So the basis will be 0, 1, 1, 0, 1, 0.
Okay.
What would be the basis of Radiance basis?
Whatever basis we're working, the standard basis. Does this make sense?
Yeah.
Why? Maybe.
When you multiply with identity.
It's the identity. This is a transformation that's
Cannot
literally going to
rotate
do
it.
nothing. Every vector will map to itself. Every vector is not going to move. No vector is going to change direction. Everyone's going to be scaled by 1. Right? So literally every vector in the plane is going to be an eigenvector because they're all not going to be doing anything. Right? If you take 1, 0, 0, 1 times xy, you get xy. Right? All vectors are going to be scaled by 1. Therefore, all vectors are eigenvectors. Right? So all vectors are eigenvectors here. Because you have a transformation that doesn't do anything. So, don't be scared. That's fine. Some transformations change things, some don't change much at all. Other questions?
So what do you say that if you don't get a solution for lambda? You say there's no vectors or eigenvectors?
There'll always be a solution for lambda, technically. Right? This will give rise to a polynomial. You always have solutions for a polynomial. You might have complex solutions, which we're not going to deal with, but I'll ignore those. I'll just give you the real ones.
So what do
I
you
wouldn't
want?
worry about it.
Professor, can you
So you'd actually have I in the components here, like a complex number. That's actually fine. But there are a lot of subtleties with complex numbers that I don't want to get into. So as far as this is concerned, I'll always give you some that has real solutions. Right. But you'll have a polynomial, so technically you'll always be able to solve for a lambda. All polynomials have solutions in the complex number. Other questions? What proof?
Number 28, which says, with the same 5.1, prove the characteristic equation of a 2 by 2 matrix A can be expressed as lambda squared minus a trace of A lambda plus determinant of A equals 0.
Okay. Yeah, I mean, in chapter 5, I don't think the proofs are going to be crazy. Like, I wouldn't actually approve from chapter 5, I don't think.
And then we'll skip it then.
There was one which I emailed you the solution to. It sort of mixed chapter 5 with chapter 4. So it's actually about being an eigenvalue of a linear transformation, and then actually do a proof on that. But the proof is really mostly based on the linear transformation. It's not based on the eigen stuff. Yeah. To get to a point where you can do some nice proofs with eigenvalues, you have to go really far. You have to go to like the spectral theorem and talk about orthonormal bases and all sorts of craziness. But yeah, proofs would be similar to like, they're going to be similar to like the ones on test 2. I don't really have one off the top of my head. Yep.
Maybe number 37 from 8.2. It says if V and W are finite dimensional vector spaces such that dimension of W is less than dimension of V, then there is no one-to-one linear transformation.
Okay, so this is the 5.1?
8.2.
8.2 problem.
37.
Prove if VW are vector spaces.
Are finite dimensional vector spaces
Okay.
such that dimension of W is less than the dimension of V, then there is no one-to-one linear transformation.
Then there is no
One-to-one
linear transformation.
And then it says let dimension of V equal M, the dimension of V.
Let dimension V equals M and dimension of W equals
N.
N. Okay, what's the proof for this? Ideas?
Because of, we learned something earlier. How do I say? I don't know how to say this.
There's no one-to-one linear transformation from who to who?
V to W.
From V to W. Okay, so let L be a transformation from V to W. What can we say? Yeah.
Alright. So there was this picture in the textbook, like where you have like for V you have like a blue square, and then for W you have like a gray square. And they said if it's not one-to-one, that means not all V would be mapped directly into W. So then that means there would have to be what's called linear combination. I don't know how to draw this. I don't know how to say this. It's like, okay, like it's like you draw a square, right? And it's like, yeah, just go with this, right? Draw a square. Like that'd be V, right? And say it's like 4 by 4, right? like this imagines the space, right?
Okay.
So it's like 4 by 4, and you have B, which is like a 2 by 2,
Okay.
right? So if this was 1 to 1, and you had a linear transformation mapping V to W, then when you map it, the image of V onto W should have all the elements of V and W, right? So if that's not the case, then that means you would have to shrink, when the linear transformation is done, then that means it would have to be, oh my god.
Guys overlapping. Think of it that way is actually kind of complicated. Because, for example, if I say this is R4 and that is R2, technically they have the same number of elements, right? So there is a one-to-one function that exists. You just have to prove it's not a linear function. It's a lot easier than you might think. With, let's say, a dimension of V equals M, dimension of W equals N, then we can express L as, what do I want to express L as?
RM to Rn, right?
Sure, I can think of this as that, yeah, but how do I write it down? How could I express this? Using a tool that we're very familiar with, so that we can
Linear.
a matrix, right? We can express L as a matrix. What size would the matrix be? These are the given dimensions. So I'm going from an m-dimensional vector space to an n-dimensional vector space, which means this is the inputs, these are the outputs.
N by N.
So it's an n by m matrix. Right? Remember the input dimension tells you the number of columns, the output dimension tells you the number of rows. Right? So since n, I know that m is greater than n, we have more columns than rows. Why is that a problem?
Free variables.
We have free variables. Right. Because if I try to find the reducer echelon form of this guy, at most I can have n pivots. It will be less than the number of columns. Not all columns will have pivots, which means I'll get a free variable if I set up a homogeneous system. Why is that bad?
North is not 0. Kernel.
Then the kernel has other things other than 0. This means, let me just write it down. If I define L of x to be a matrix A times x, where A is n by n, then the kernel of A will not be just the 0 vector. I'll have free variables, which means I'll have infinite number of solutions. And this means L is not 1 to 1. Because we had a theorem that says if it's 1 to 1, if and only if the kernel is only the set containing the 0 vector. So those theorems that I gave you guys that, oh, the following are equivalent, this means this and this means that, those are the really important ones. Those are what's going to really get you to the answer. So when you want to use one of those guys, they're all about matrices. So if you hear about a linear transformation, figure out a way to get it to a matrix, right? Because once you know everything about that matrix, you know about that linear transformation, right? Whether it's 1 to 1 or onto, especially if it's square, just knowing the determinant gives you so much information. Right? So a lot of the proofs are going to involve things like that, right? So if I give you a linear transformation, figure out how it works in matrices, be able to change bases if you have to in order to prove something. But knowing about matrices and knowing those theorems that talks about things being equivalent. That's basically what's going to get you there. So thinking in terms of pictures, like, oh, there's a box over here and a box over there, it's useful a lot of the time, but here I don't think it would be useful enough because the respective sizes of things, like the sizes of sets can be the same, but their dimensions are not. And so when you draw a picture, the size intuition might be off. Right? You can have spaces of different dimensions that have the same number of things. So you might think that, oh, I should be able to connect them one to one, but not with a linear transformation. Right? It'll have to be some other kind of function that will connect them one to one. Doing with a linear transformation, you need certain things to match up. You need dimensions to match up because you need to have as many pivots as you have columns. That's it. I mean, if you practice the kinds of things that I mentioned, I don't think the last test will be hard. 2/3 of it anyway should be super easy because it's all computation. Those ones, the eigenvalues, eigenvectors, it's computation. The basis question, it's all computation. I'll give you one question where I throw in a couple of proofs. They shouldn't be more complicated than this one. It's just really going to be testing, do I know what this means? Do I know how to translate this into a language that I can understand to apply? Right? And a lot of it, again, it's going to come down to, can you figure out a convenient way to turn this into a matrix? Right? And you'll see that one of the questions on the final, it had that. This is why the chapter on isomorphisms was so important, because it gave you a way that you can get to matrices out of nowhere. So in chapter, on one of the tests, there was something that says, it gave you the basis of sine t and cosine t, right? It said that was a basis, right, for some space, right? Which means every v in that vector space could be expressed as. And it gave you some weird linear transformation too. It said like, there's a linear transformation on the functions where L of f of t gives you f of t plus 2f prime plus 3f double prime. And you might wonder, oh, calculus, what do you do? I don't remember how to differentiate. Right, all these sorts of stuff. And you're like, what do these guys even look like? The important thing is, you don't need to know what they look like because you just translate to vectors. So I know that every v in this could be expressed as v equals c1 sine t plus c2 cosine t, right? Now I just consider this an ordered basis, and so basically what I can do is I can just think of this as a 2D vector, right? So I don't think of moving functions around, I now think of moving two-dimensional vectors around, right? Where my first coordinate is the coefficient of the sine, my second coordinate is the coefficient of the cosine. I can turn these guys into columns and throw them into matrices. And once I have things in matrices, I can do anything. I have all these theorems at my disposal, right? So you wouldn't want to think of things in this way. Think of them in this way, because you know how to deal with this. Right? So a lot of it comes down to expressing it isomorphically to a set of vectors, right? So I don't think of things as a linear combination of sines and cosines. Think of them as 2D vectors, right? And I can look at what a basis might look like and what this might look like, right? So I actually did a full solution for this problem, so you can see what I did. And when you're reading it, it's going to look insanely confusing, but when the solution was actually pretty short. You'll realize that once you translate to this, it's really not that bad. Figure out how to get to a matrix. And know the theorems that have to do with matrices, those ones that says the following are equivalent. If you know all those, you'll be fine. For now, we'll stop there. If you have any more questions, I can answer them after, but we need to do the surveys. I need a volunteer.
5 extra points.